Welcome to the deep dive. Today, we're really getting into something profound, almost legendary in physics. It's about Albert Einstein's later years, his relentless search for one single idea, a unified field theory.
That's right. He was hunting for this elegant framework that could describe all of nature's forces together.
And it wasn't just about the math, was it? It was deeper, a belief that at its core, the universe must be simple, beautiful even.
Exactly. That drive, that conviction that underneath it all, there's a unifying principle.
Yeah.
Well, that's really the engine pushing theoretical physics forward even today.
So that's our mission for this deep dive, to explore this fundamental clash we have in physics right now.
Yeah, because we're in this strange situation. We have two incredible theories, general relativity, or GR, for the big stuff.
Gravity, black holes, the universe expanding.
Right. And then quantum mechanics, QM, for the tiny stuff,
Yeah.
atoms, particles, all that weird quantum fuzziness.
Yeah.
Both work brilliantly in their own domain.
But they don't work together. They're fundamentally incompatible.
Utterly. And today we're digging into why they clash and how this candidate, string theory, proposes to fix it. And it does so by, well, basically rewriting our understanding of everything space-time matter itself.
So where does this incompatibility really show up?
It explodes really in the most extreme places you can imagine. Think about the very first instant of the Big Bang. Or picture diving deep inside a black hole, right into the singularity.
Places where you have immense gravity, like GR describes, but crammed into a minuscule space, which is QM's territory.
Precisely. You need both theories simultaneously in those spots. And when you try to apply both sets of equations, they just break.
You get nonsense answers, right? Infinities popping up everywhere. I read one description saying the equations shake, rattle, and gush with steam.
That's a pretty good way to put it. It signals a complete breakdown. The math tells you your framework is wrong, fundamentally wrong, at that scale.
So it forces this question. Is the universe just inherently split? One rulebook for planets and another totally contradictory one for electrons.
String theory is basically the leading attempt, maybe the only comprehensive attempt right now, to say, no, absolutely not. It argues there is a single underlying reality.
Okay, let's unpack the history here a bit. This isn't the first major conflict physics has faced. We had one before GR involving Newton.
Right, Newton's theory of gravity, I mean, it worked incredibly well for centuries, predicts planetary orbits, apples falling, fantastic stuff.
But it had this weird feature baked in, action at a distance, instantaneous action.
Exactly. According to Newton, if the sun just vanished, poof, the Earth would instantly feel the loss of its gravity and fly off into space.
Even though the light from the sun, the visual information that it's gone, wouldn't reach us for 8 minutes.
That was a huge problem, especially after Einstein's earlier work, special relativity, in 1905.
Because special relativity established the cosmic speed limit, right? Nothing travels faster than light. No information, no influence, nothing.
So Newton's instantaneous gravity had to be wrong. It violated Einstein's own principle. That set the stage for general relativity.
And Einstein's solution in 1915 was radical. He completely reframed gravity.
He did. It's not some invisible force pulling things across space. It's the geometry of space-time itself. Mass and energy actually warp the fabric of space and time around them.
So space and time aren't just a static background, they're active participants.
Dynamic players, exactly. And when mass moves, it creates ripples in this fabric, gravitational waves that travel outwards at the speed of light. Problem solved. It respects the cosmic speed limit.
It's such a shift. From a mysterious pull to pure geometry. And the key insight was his happiest thought, the equivalence principle.
Ah, yes. That's a brilliant piece of reasoning. Basically, it says that locally, you can't tell the difference between being in a gravitational field and being in an accelerated frame of reference.
Like being in a windowless elevator accelerating upwards in empty space feels exactly the same as standing still on Earth.
Precisely. If you drop something in the accelerating elevator, it falls to the floor just like it does on Earth.
Yeah.
So gravity and acceleration are, in a sense, equivalent.
And since acceleration can be described using the mathematics of curved spaces,
And gravity must be the curvature of space-time. That's the leap.
the classic analogy helps here, the bowling ball on the rubber sheet.
It does. The heavy ball creates a dip, a curve, in the sheet. That's space-time being warped by mass. Then if you roll a marble nearby,
It doesn't go straight. It follows the curve created by the bowling ball.
it follows the path of least resistance, the straightest possible path in that curved space.
Yeah.
And we see that curved path and call it gravity.
It's not being pulled, it's just following the contours. I love that John Wheeler quote that sums it up.
Oh, the mass grip space one.
Yeah. Mass grips space by telling it how to curve. Space grips mass by telling it how to move.
Perfect summary.
Mhm.
Elegant. Beautiful. GR is a masterpiece.
Okay, so GR solves the speed of light problem and gives us this elegant geometric picture of gravity. But then we zoom way, way down.
And we hit the brick wall of quantum mechanics. The world of the very small operates under entirely different rules. Very strange rules.
Let's start with just the ingredients list. What are the fundamental particles, according to our best current theory, the Standard Model?
Well, after decades of smashing things together in particle accelerators, we found this sort of zoo. There's the electron, familiar enough. Then there are 6 types of quarks. They have weird names like up, down, charm, strange, top,
They
bottom.
make up protons and neutrons, right?
Mostly the up and down quarks, yes. Then you have the electron's heavier, unstable cousins, the muon and the tau, and 3 types of very light, very elusive particles called neutrinos.
It feels arbitrary. Why these specific particles? Why 6 quarks? Why 3 families of particles that seem like heavier copies of each other?
That's exactly the problem. The Standard Model describes what is there brilliantly, but it doesn't explain why. It feels like a list, not a fundamental explanation. I think it was I. Rabi, the Nobel laureate, who famously said when the muon was discovered.
Oh, yeah. What did he say?
Who ordered that?
What?
It just didn't seem necessary. It didn't fit the pattern they expected.
Yeah. Okay, so that's the matter side. Then you have the forces.
4 fundamental forces. We have gravity, which the Standard Model doesn't really incorporate. That's GR's job. Then electromagnetism, carried by the photon.
Light, radio waves, magnets.
Right. Then the strong nuclear force, holding atomic nuclei together, carried by gluons. And the weak nuclear force, responsible for certain types of radioactive decay, carried by particles called W and Z bosons.
Again, a list. And these forces have wildly different strengths and ranges. Why? The Standard Model gives us the what, but not the why.
Exactly. It's incredibly successful experimentally, but it leaves these deep questions unanswered. And the quantum rules underpinning it all started with another crisis, another mathematical disaster.
This was Max Planck, right? Around 1900.
Yes. Classical physics predicted that any hot object, like a simple black box or an oven, what physicists call a black body, should radiate energy at all frequencies. The problem was the math said it should radiate an infinite amount of energy, especially at high frequencies in the ultraviolet range.
The ultraviolet catastrophe. Obviously, ovens don't glow infinitely bright.
Obviously not. So Planck made this radical guess. He proposed that energy couldn't be emitted or absorbed smoothly, continuously. It had to come in little packets, discrete chunks. He called them quanta.
And the energy of each chunk, each quantum, was tied to the frequency.
Directly proportional, yes, via a new fundamental constant, now called Planck's constant, Ibardi. So high-frequency light required a big chunk of energy just to be created.
And in a normal oven, there just wasn't enough total heat energy available to make lots of those really high-energy packets.
Exactly. It effectively choked off the high-frequency radiation, fixing the calculation. The math suddenly matched reality perfectly. It was revolutionary, the birth of quantum theory.
And Einstein picked up on this quantum idea 5 years later for the photoelectric effect.
He did. He argued that light itself isn't just a wave. It's actually made of these energy particles, photons. The energy of a single photon depends on its frequency, its color.
Which explained why, say, dim blue light could knock electrons off metal, but really bright red light couldn't.
Right. The blue light photons had enough individual energy per packet, even if there weren't many of them. The red light photons, no matter how numerous, simply didn't have the necessary kick individually. It cemented the idea that energy is quantized.
And this leads to maybe the most famous quantum weirdness, wave-particle duality.
Yeah, this is central. Things at the quantum scale, like electrons and photons, somehow manage to be both particles and waves at the same time.
How do we even see that?
Well, you detect them as particles, you get a click on a detector at a specific point. But their behavior, especially when you're not looking, is wave-like. The classic demonstration is the double-slit experiment.
Yes. You fire particles, let's say electrons, one by one, towards a barrier with 2 narrow slits in it.
Right. Now, if electrons were just tiny bullets, you'd expect 2 bands on the screen behind the barrier, lined up with the slits.
But that's not what happens.
Not at all. Even firing them one at a time, slowly, they build up an interference pattern on the screen, stripes of many hits and stripes of no hits.
Which is what happens when waves overlap, right? like
Yeah.
ripples and water interfering, canceling in some places, reinforcing in others.
Exactly. It's undeniable wave behavior. But how can a single electron, going through presumably one slit or the other, interfere with itself?
It somehow has to know about both slits. It acts like a wave spreading through both, even though it's detected as a single particle.
It's deeply strange. Richard Feynman said it contains the central mystery of quantum mechanics. The electron doesn't have a definite path. It exists as a wave of possibilities until you measure it. Then it snaps into being a particle at one location.
Okay, weirdness established. Now, how does this weirdness crash into gravity? There's one more piece, right? Heisenberg.
Yes, Werner Heisenberg and the uncertainty principle. This is fundamental. It states that there's a built-in limit to how precisely you can know certain pairs of properties for a particle simultaneously. The classic pair is position and momentum, or velocity.
The more you pin down exactly where it is,
The less precisely you can know how fast it's going, and vice versa. There's an inherent fuzziness, a limit imposed by nature itself, related to Planck's constant again.
and this uncertainty isn't just about measurement limitations, it's fundamental to reality.
Yes, and it has staggering consequences for the vacuum of space. Because energy and time are also an uncertainty pair, energy itself is uncertain over very short timescales.
So even in empty space.
Energy can be borrowed from the vacuum, thanks to 1 mc2, allowing pairs of particles and antiparticles, like an electron and a positron, to spontaneously pop into existence.
Virtual particles.
Virtual particles
Yeah.
exist for an incredibly fleeting moment, borrowing that energy, and then they annihilate each other, paying the energy back. The vacuum is not empty. It's this teeming, chaotic, frenzied soup of quantum activity.
Okay, I think I see where this is going. What happens when you apply this quantum uncertainty to gravity itself?
Disaster. Gravity, according to GR, is the curvature of space-time. But if energy and momentum are uncertain at tiny scales, then the curvature of space-time must also be uncertain and fluctuating wildly.
So if you zoom down to the tiniest possible scale, the Planck length, that's 1033 centimeters, unbelievably small.
The uncertainty principle implies that space-time itself isn't smooth anymore. It becomes this churning, distorted, warped mess. Physicists call it quantum foam.
The smooth geometry that general relativity absolutely relies on is just gone.
Completely obliterated. The assumptions of GR break down. And if you try to do calculations using quantum field theory where gravity is treated like the other forces, involving point-like graviton particles interacting in this foam, the math just explodes. You get infinite probabilities, infinite energies. It's mathematical nonsense.
So that's the core conflict. Quantum foam destroys smooth spacetime. GR needs smooth spacetime. They can't coexist at the Planck scale.
That's the fundamental clash.
All right, crisis identified. Smooth GR meets choppy QM, and it's chaos. Now, enter string theory. What's the big idea here? How does it propose to fix this?
The core idea is surprisingly simple, almost disarmingly so. It suggests that the fundamental constituents of nature aren't zero-dimensional points like we assumed for electrons and quarks.
They're not dots.
No, they are tiny one-dimensional loops or filaments, strings, vibrating strings, and they are incredibly small, roughly the size of that Planck length we just mentioned, 1033 centimeters.
So everything, electrons, quarks, photons, they're all just different vibrations of the same basic string.
Exactly. Think of a violin string. Pluck it one way, you get one note. Pluck it differently or change the tension, you get a different note. In string theory, the different vibrational patterns of these fundamental strings correspond to the different particles.
So an electron is one note, a quark is another, a photon is another.
That's the idea. It potentially unifies all these seemingly arbitrary particles in the standard model as just different resonances of one underlying object. It turns particle physics into, well, the music of the cosmos, as it's sometimes called.
Okay, that's elegant conceptually. But how does changing points to loops solve the clash between GR and QM?
It's all about that extension, that size. The string isn't a zero-dimensional point. It has a tiny but non-zero length.
And that helps because
Because it effectively smears out the interaction. Remember how point particles interacting within the violent quantum foam led to infinities? The string, being slightly spread out, doesn't probe space-time at an infinitely small point.
it sort of averages out the most violent, tiny fluctuations.
In a sense, yes. It smooths over those problematic ultra-microscopic distances. When you calculate interactions using strings instead of points, the disastrous infinities that plague the old approach just cancel out. The math gives sensible, finite answers.
Wow. So the extended nature of the stream inherently resolves the conflict.
It's the core mathematical achievement. It allows quantum mechanics and gravity, in the form of curved spacetime to coexist peacefully.
Now, what about gravity itself? Does string theory just accommodate it, or is it more fundamental?
This is crucial. String theory doesn't just allow for gravity, it requires it. When you analyze the possible vibrational patterns of the string, one specific pattern inevitably emerges from the mathematics.
And that pattern has the properties of.
Exactly, the properties required for the hypothetical quantum particle that carries the gravitational force. It has the right spin, zero mass. It fits perfectly. So string theory isn't just compatible with gravity, it naturally predicts gravity's existence at the quantum level. It is a quantum theory of gravity.
Okay, that's a huge claim. Now, I know there's another key ingredient needed to make the whole theory mathematically sound. Supersymmetry or QSY?
Ah, yes, supersymmetry. This one can seem a bit strange at first glance.
Because it doubles the number of particles, right? It proposes that every known particle has a heavier superpartner with a different spin. Like an electron has a selectron, a quark has a squark.
That's right. Every fundamental particle we know of is either a fermion, matter particles like electrons, quarks, or a boson, force carriers like photons, gluons. Supersymmetry postulates a fundamental symmetry between these two types, pairing every fermion with a boson partner and vice versa.
Why add all this complexity if the goal was unification and simplicity?
It's about mathematical consistency and solving some deep problems within the standard model itself, particularly something called the hierarchy problem.
Okay, what's the hierarchy problem?
It's about the enormous gap in energy scales. We have the scale where forces like electromagnetism and the weak force operate, characterized by particles like the Higgs boson. Then there's the incredibly higher energy scale where gravity becomes strong, the Planck scale. The gap is huge, about 10/15s different.
And why is that gap a problem?
Because in quantum field theory, particles interact with those virtual particles, constantly popping in and out of the vacuum. These interactions contribute energy, or effectively mass, to particles like the Higgs boson.
And the contributions are massive.
Enormous. The math suggests these quantum jitters should naturally drag the Higgs mass all the way up to the Planck scale, but we measure the Higgs mass to be vastly lighter.
So the standard model only works if you assume these huge quantum contributions somehow magically cancel each other out almost perfectly, like to 15 decimal places.
Precisely. It requires an unbelievable amount of fine-tuning. It seems unnatural, like balancing a pencil on its tip. Supersymmetry offers a natural solution.
How?
Because fermion and boson loops in these quantum calculations often contribute with opposite signs. Supersymmetry pairs every fermion with a boson. So the huge positive contribution from a particle loop is almost exactly canceled by the huge negative contribution from a superpartner loop.
Like a seesaw balancing out perfectly.
Exactly. The cancellations happen automatically because of the symmetry, protecting the Higgs mass and keeping it naturally light without any ridiculous fine-tuning. It stabilizes the theory.
So SUSY is essential for consistency. Does it offer any other sort of evidence?
It does offer a really suggestive hint towards unification. If you take the measured strengths of the three non-gravitational forces, strong, weak, and electromagnetic, and extrapolate how they change with energy.
In the standard model, they get closer but don't quite meet at one point, right?
Correct. They almost unify. But if you add the effects of all the supersymmetric particles into the calculation, it changes how those force strengths run with energy. And with SUSY included, they converge beautifully, meeting precisely at a single point at very high energy, near the Planck scale.
Wow. Okay, so it suggests that those three forces really were unified into a single force in the very early, hot universe.
It's a strong piece of circumstantial evidence. It makes the picture much more elegant and hints that SUSY might be a real feature of nature, even if we haven't directly detected those heavy superpartners yet.
Okay, so strings fix the GRQM clash, and SUSY helps make it consistent. Now we get to maybe the wildest part, the extra dimensions. String theory doesn't work in just 3 spatial dimensions.
No. Mathematically, for the theory to be consistent, particularly regarding its quantum properties, it requires more spatial dimensions. The most developed versions, superstring theories, operate in 9 spatial dimensions plus 1 time dimension, so 10 space-time dimensions in total.
10 dimensions? Where are the other 6? We definitely only experienced 3 spatial ones, length, width, height.
This sounds crazy, but the idea actually goes way back, even before quantum mechanics was fully formed, to a physicist named Theodore Kaluza in 1919.
What did Kaluza propose?
He was trying to unify Einstein's general relativity, which was brand new then, with the other known force at the time, electromagnetism, described by Maxwell's equations. He had this wild idea. What if space-time had 4 spatial dimensions, not 3?
So 5 dimensions total, including time.
Right. He wrote down Einstein's equations for gravity in 5 dimensions. And when he worked through the math, an amazing thing happened. The equations naturally split into 2 sets. One was just standard GR in our usual dimensions. And the other set,
Let me guess.
Maxwell's equations for electromagnetism, that just popped out of the geometry of the extra dimension. It was an astonishing unification achieved just by adding 1 dimension.
But again, where is that extra dimension?
That part came a few years later from Oscar Klein.
Mm-hmm.
He suggested the extra dimension could be real, but curled up, or compactified, into an incredibly tiny circle, far too small for us to see or probe directly.
Like the garden hose analogy. From far away, it looks like a 1D line, but up close you see the 2D surface, with one dimension being the length and the other being the tiny circular girth.
Exactly that analogy. We might be living on the long part of the hose, unaware of the tiny curled-up dimension. String theory takes this Kaluza-Klein idea and ramps it up. It needs 6 extra spatial dimensions to be curled up.
6 dimensions, all curled up, incredibly small. What shape do they take? Are they just tiny circles?
Probably not simple circles. For string theory, to reproduce the particles and forces we see in the standard model, these 6 dimensions need to be curled up into very complex, intricate geometric shapes. They're known as Calabi-Yau manifolds or Calabi-Yau shapes.
Calabi-Yau. What do they look like?
It's hard to visualize properly as they exist in 6 dimensions, but mathematically, they are complex spaces that have specific properties needed for string theory. They can be highly convoluted, containing holes and handles, sort of like multidimensional donuts or pretzels, but much more complicated.
And here's the mind-blowing part I read about. The exact shape of these tiny hidden dimensions determines the physics we see.
That's the crucial link. The geometry of the Calabi-Yau space, how it twists, how many holes it has, the size of those holes dictates the possible ways strings can vibrate within it.
And since string vibrations correspond to particles,
the geometry determines the fundamental properties of those particles. The mass of the electron, the charge of the quarks, the strengths of the forces. These numbers, which seem arbitrary in the standard model, are supposedly encoded in the precise shape of these curled-up dimensions.
So if we knew the exact shape of our universe's hidden dimensions, we could, in principle, calculate all the fundamental constants of nature from first principles.
That's the ultimate dream of string theory. Physics becomes geometry.
But you said there are shapes, plural. How many possible Calabi-Yau shapes are there?
That's a big challenge. There isn't just one possibility. Mathematicians estimate there could be tens of thousands, maybe hundreds of thousands, or even vastly more distinct Calabi-Yau shapes that satisfy the consistency conditions.
And each different shape would lead to a different universe, with different particles and forces.
Potentially, yes. This vast number of possibilities is often called the string theory landscape. It raises a huge question. Why this particular shape for our universe? Why these laws, these particles? Did we just get lucky? Or is there some principle that selects the right one? We don't know yet.
That feels like it reintroduces the arbitrariness we were trying to escape. Let's move to another strange geometric feature, something called T-duality. It messes with our notion of size.
T-duality is uniquely stringy. It has no counterpart in theories based on point particles. Let's use that simple Kaluza-Klein idea again. Imagine one extra dimension curled up into a circle of radius r.
Okay, it's a simple circle.
T-duality states that the physics described by string theory in this space is exactly identical to the physics in a space where the circle has a radius of $1, assuming r is measured in fundamental Planck units.
Wait, a universe with a large circular dimension is indistinguishable from one with a tiny circular dimension. How can that be?
It comes down to the ways strings can carry energy in that dimension. A string can vibrate. That's one kind of energy mode. Higher energy vibrations correspond better to smaller circles, like high notes on a shorter violin string.
Okay, vibration modes.
But a string can also wind around the circular dimension, like wrapping a rubber band around your finger. The more times it winds, the more energy it has. And this winding energy is greater for larger circles.
So vibration energy goes up as size goes down, winding energy goes up as size goes up.
Exactly. T-duality shows that if you swap R for $1, the spectrum of possible vibration energies in one picture perfectly matches the spectrum of winding energies in the other picture, and vice versa. The total set of possible energies, which determines all the physics, is identical.
So you literally cannot tell the difference between a universe with radius r and one with radius 1r.
From the perspective of a string, no. They are physically equivalent.
What does that imply for, say, the Big Bang? Can the universe shrink down to zero size?
Key duality suggests no. It implies there's a minimum effective size in string theory, related to the Planck length. If you tried to squeeze a circular dimension smaller than this scale, the physics would just look like it was getting bigger again, due to the dollar duality.
So the Big Bang singularity, that point of infinite density and zero size, might be avoided. The universe might have bounced instead of starting from nothing.
It's a profound possibility offered by string theory. It fundamentally alters our picture of the universe's beginning, replacing this singularity with something governed by string physics and a minimum length scale.
Okay, beyond messing with distance, string theory also seems to allow space-time itself to tear. I thought that was forbidden.
In classical general relativity, yes. Changing the topology of space, like ripping a hole in it or patching one up, was thought to inevitably lead to physical infinities, a singularity. It would be catastrophic.
But string theory handles it.
Remarkably, yes. Calculations in string theory showed that the fabric of spacetime can tear and repair itself in certain ways without disaster. These are processes called flop transitions or conifold transitions.
What happens during one of these transitions?
Essentially, one Calabi-Yau shape can smoothly transform into another Calabi-Yau shape that has a different topology, maybe a different number of holes. Think of smoothly morphing a donut into a beach ball. String theory provides the mathematical framework where these kinds of transitions are perfectly well behaved.
So the very structure, the topology of the hidden dimensions might not be fixed, it could change.
It suggests that space-time geometry is even more dynamic than we thought, allowing for transformations that were previously considered impossible.
That's incredible flexibility. Let's finish this part with what many consider one of string theory's biggest successes: black hole entropy.
Right. This was a huge puzzle dating back to the 1970s, work by Jacob Bekenstein and Stephen Hawking. They discovered, using arguments combining GR and quantum ideas, that black holes must have entropy.
Entropy meaning disorder or the number of internal states.
Exactly. And the amount of entropy they calculated was enormous, proportional to the area of the black hole's event horizon. But the question was, entropy of what? Classically, a black hole is incredibly simple, defined just by its mass, charge, and spin. Where does all that internal disorder come from? What microscopic constituents are being rearranged inside?
GR gave no clue.
None whatsoever. For about 25 years, it was a deep mystery. Then, in 1996, Andrew Strominger and Kamran Vafa, using string theory.
They tackled a specific type of black hole.
Yes, certain mathematically tractable black holes called BPS, or extremal black holes. Within string theory, they could model these black holes as specific, complicated configurations of strings and other objects called D-branes, which are like higher dimensional membranes.
So they built a microscopic model of the black hole using strings and branes.
Precisely. And the crucial step was, using the rules of string theory, they could then count the number of ways to arrange those strings and branes that would result in a black hole with the same mass and charge. This counting is, by definition in statistical mechanics, the entropy.
And the number they got.
Matched the Bekenstein-Hawking formula exactly, including all the numerical factors. It was a stunning success.
Wow. So string theory provided the microscopic explanation for the black hole's disorder. It identified the atoms of the black hole, so to speak.
That's a good way to think about it. It showed that strings and branes could be the fundamental constituents whose arrangements account for the black hole's thermodynamic properties. It's considered one of the most powerful pieces of evidence that string theory is on the right track as a quantum theory of gravity.
Okay, let's try to pull this all together. It's been quite a journey through some pretty abstract territory.
It definitely goes beyond everyday intuition.
We've seen how string theory proposes replacing point particles with tiny vibrating strings. This simple change seems to elegantly resolve the deep conflict between general relativity's smooth spacetime and quantum mechanics' fuzzy uncertainty.
Right. The string's extension smooths out those problematic infinities. And critically, it naturally incorporates a quantum description of gravity. The graviton just appears as one of the string's vibrational modes.
Then we layered in supersymmetry, which seems necessary for mathematical consistency, helps solve the hierarchy problem by stabilizing the Higgs mass, and even gives this beautiful hint that the other forces unify at high energies.
Check. And then the really mind-bending part, the extra dimensions. String theory needs 6 extra spatial dimensions curled up into complex Calabi-Yau shapes.
And the geometry of those hidden dimensions somehow dictates the fundamental constants of nature: particle masses, force strengths. Physics is geometry.
That's the profound implication. We also saw weird effects like T-duality, suggesting a minimum length scale and potentially resolving the Big Bang singularity and even space-tearing transitions being allowed.
And finally, that remarkable success in explaining black hole entropy by counting the arrangements of strings and branes. It's an impressive theoretical structure.
It truly is. The way it hangs together connects different areas of physics, solves long-standing problems. It's deeply compelling to many physicists.
Yeah.
But we absolutely have to acknowledge the challenges ahead.
Right. The biggest elephant in the room is experimental verification, isn't it? These strings are too small, the energy's too high to probe directly.
That's the primary hurdle. We can't build a Planck-scale accelerator. So physicists are increasingly looking to cosmology. The early universe was the ultimate accelerator.
So, looking for faint signatures left over from the Big Bang. In the cosmic microwave background radiation, maybe subtle patterns in the distribution of galaxies, or perhaps specific types of gravitational waves.
Exactly. We need to use the universe itself as our laboratory. It's often called the cosmological accelerator. We search for relics, fossils from that initial Planck era when string effects would have been dominant.
And there's still that landscape problem. If there are countless possible Calabi-Yau shapes, leading to countless possible universes with different laws, how do we explain why our universe is the way it is?
That's a huge conceptual challenge. Does it mean the laws we see are just an environmental accident, like the specific temperature of Earth being right for water? This leads some towards multiverse ideas and the anthropic principle we observe this universe because it's one of the few where observers can exist.
Which feels a bit unsatisfying to some, perhaps, like giving up on finding a truly fundamental explanation.
It does to many. The hope remains that there's a deeper principle we haven't found yet, maybe some dynamic mechanism that selects the correct Calabi-Yau vacuum, or perhaps the landscape isn't as vast as it seems, or maybe M theory, a more encompassing framework related to string theory, holds the key.
It brings us back to that initial quest for unification, for the ultimate why. We've seen how principles of symmetry seem fundamental to our current laws. Relativity, gauge symmetries in the standard model. And string theory seems to underlie those symmetries.
That's right. The symmetries that we observe seem to emerge from string theory. But the question then becomes, what principle underlies string theory itself? Is there some ultimate foundational idea that dictates that reality must be described by vibrating strings in 10 dimensions?
Like Einstein finding the equivalence principle led inevitably to GR, we're searching for the guiding principle for string theory.
Exactly. If we could find such a principle, one that uniquely points to this theory, then perhaps the universe had to be this way. All the parameters, all the laws wouldn't be accidental, but necessary consequences of that ultimate logic.
And that leads to a final, really profound thought. If the ultimate theory removes all choice, establishes that the universe is the way it is out of absolute logical necessity, could it finally address that oldest philosophical question, the one Leibniz asked?
Why is there something rather than nothing?
Yeah. Could a truly final theory provide a scientific basis for understanding existence itself?
That might be the ultimate prize. Whether string theory or whatever succeeds it can reach that far. Well, that remains the driving question for the next generation. It's quite a thought to leave our listeners with.